Gravity is a force. Mass pulls on mass. The bigger the mass, the stronger the pull. You learn this in school, you feel it in your bones, and Isaac Newton himself wrote the equation. It is, without exaggeration, one of the most successful ideas in the history of science. For over 200 years it predicted the motion of planets, the tides of the oceans, the paths of cannonballs and comets. Nobody had a single reason to doubt it, and it is completely wrong. Not a little wrong. Not needs a small correction wrong. The entire picture, the idea that mass reaches out across empty space and tugs on other mass, is a fiction. A brilliant, useful, magnificent fiction that gets the right answer 99% of the time, but a fiction nonetheless. And by the time I am done here, you will not be able to see gravity the same way again. You will not want to, because the truth is so much stranger, so much more beautiful, and so much more unsettling than anything Newton ever imagined. Let me start by making you comfortable. Let me remind you how extraordinarily good the whole idea is. I want you to feel safe with it first, because if you do not appreciate how strong the building is, you will not appreciate what it means when the foundation cracks. You drop a ball, it falls. Why? Because the earth has mass, the ball has mass, and there is a force between them. Newton told us exactly what that force is. You multiply the two masses together, divide by the square of the distance between their centers, and stick a constant out front. G, the gravitational constant, about 6.67 times 10 to the minus 11 in standard units. Gravitational force equals G times mass 1 times mass 2 divided by distance squared. That equation is a miracle, not a metaphorical miracle, and that a practical one. You can use it to predict to staggering accuracy where the moon will be next Thursday, where Jupiter will be next century, where a satellite launched from Florida will end up 3 days from now. We used it to find Neptune. Think about that. In the 1840s, astronomers noticed that Uranus was not quite following the orbit Newton's equation predicted. It was wobbling, drifting just slightly off course. Instead of blaming the equation, they said, something we cannot see must be pulling on it. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where this invisible body had to be. Le Verrier sent his prediction to an astronomer in Berlin, a man named Johann Galle. On the night of September 23, 1846, Galle pointed his telescope exactly where Le Verrier said to look, and within a single hour he found Neptune, a planet no one had ever seen, conjured from ink and paper, and an equation about pulling. When a mathematical formula lets you discover planets before anyone has laid eyes on them, you tend to trust it deeply. And the picture Newton paints is clean and comforting. And space is a stage. Objects sit on the stage. Between any two objects with mass, there is an invisible thread of force, always pulling, always proportional to the masses, always getting weaker with distance. The whole universe is connected by these threads, and the threads obey a simple, elegant rule. You can draw diagrams, you can do the calculation in an afternoon. Everything makes sense. And it is not just planets and moons. Tides. The tides of the ocean rise and fall because the moon's gravitational pull on the near side of the Earth is slightly stronger than its pull on the far side. And that difference stretches the water into an elongated bulge. You can calculate the heights of those tides using Newton's equation. Engineers designing harbors and bridges have been doing it for centuries. The Voyager spacecraft used gravitational slingshots around Jupiter and Saturn, borrowing a tiny fraction of each planet's orbital momentum to fling themselves to the edge of the solar system and beyond. Every one of those maneuvers was planned with Newton's gravity. So this is not some fragile, approximate idea. This is one of the most battle-tested theories in all of science. 3 centuries of engineering triumph rest on it. And the picture it offers is deeply satisfying. Space is a passive arena. Masses sit in it like marbles on a table, and between them run invisible threads of force that obey a clean mathematical law. So where does it go wrong? It goes wrong in several places, but let me start with the one Newton himself worried about. How does the Earth know the ball is there? It sounds like a silly question, but think about it carefully. The ball and the Earth are not touching. There is no wire between them, no string, no rod, no physical connection of any kind. Between them is empty space, vacuum, nothing. And yet somehow, according to Newton, the Earth reaches across that gap and grabs the ball instantaneously, with no delay, no signal traveling back and forth, no mechanism of any kind, Newton called this action at a distance, and he was deeply troubled by it. In a famous letter to the theologian Richard Bentley, he wrote that the idea that one body could act upon another through a vacuum without any physical intermediary was so great an absurdity that no person with a competent faculty of thinking could ever fall into it. Those are strong words from the man who invented the theory. He found his own idea philosophically indefensible. But the math worked, so he published it, admitted he had no mechanism, and said he would leave that problem for future generations. Future generations mostly ignored the problem. For 200 years, physicists used Newton's equation, got the right answers, and did not ask how the pull was transmitted. Why bother? The equation works, but there were cracks, small ones, the kind you only notice if you are very careful and slightly obsessive. The first crack appeared in 1859. It involved Mercury. Mercury is the closest planet to the Sun, and it orbits in an ellipse. But the ellipse does not stay fixed. It rotates very slowly. The long axis of Mercury's orbit swings around the Sun like the hand of a very lazy clock. Astronomers call this the precession of the perihelion. Most of this precession is caused by the gravitational pulling of Venus, Jupiter, and the other planets. You can calculate each planet's contribution very precisely. Leverrier did exactly that, and the numbers did not add up. After you accounted for every known planet and every known effect, there were about 43 extra arcseconds of precession per century that had no explanation. 43 arcseconds is roughly 1/100th of a degree per century, an absurdly small number. But it was persistent. Decade after decade, the discrepancy remained. Leverrier, who had found Neptune by spotting a similar discrepancy with Uranus, proposed the same solution, a hidden planet. He called it Vulcan and placed it in an orbit closer to the Sun than Mercury. Astronomers searched for Vulcan for half a century. They looked during solar eclipses when the Sun's blinding light was blocked and faint nearby objects might become visible. Expeditions were organized, claims were made and retracted. Vulcan was never found. It does not exist. The problem was not a missing planet. The problem was deeper than that. The second crack was conceptual, and it came from a young man working in a patent office. In 1905, Albert Einstein published Special Relativity. One of its central conclusions is that nothing, absolutely nothing, can travel faster than the speed of light. Not matter, not energy, not any form of information or influence. The speed of light is not just a speed. It is a speed limit, woven into the structure of reality itself. Now consider what this means for Newton's gravity. In Newton's universe, gravity acts instantaneously. If the Sun were to suddenly vanish, the Earth would instantly feel the absence of its gravitational pull and fly off in a straight line. No delay, no transit time. The gravitational influence adjusts everywhere in the universe at exactly the same moment. But if nothing can travel faster than light, this is impossible. The information that the Sun has vanished cannot reach the Earth faster than light can. It would take about 8 minutes. During those 8 minutes, the Earth would continue to orbit a sun that no longer exists because the change in the gravitational field has not arrived yet. Newton's gravity violates the cosmic speed limit, and that is not a small technicality. That is a structural failure. So here we are. The equation gives the wrong answer for Mercury. The theory violates the speed of light, and there is no mechanism for how the force is transmitted. 3 strikes. Let me take you somewhere else entirely now. Now, forget planets. I want to put you in a box, a sealed box. No windows, no way to see outside. You are in deep space, far from any star, planet, or galaxy. You and everything inside the box are weightless. You float. Your water bottle floats. Your shoe floats. You push off one wall, drift gently across, and bump into the other wall. There is no up, no down. Every direction feels the same. Now I'd bolt a powerful rocket to the bottom of the box and ignite it. The rocket accelerates the box upward at exactly 9.8 meters per second squared. Inside the box, you feel yourself pressed toward the floor. You land on your feet. You feel heavy. Your water bottle drops. Your shoe drops. You drop a coin, and it clinks against the floor. Everything behaves exactly as it does in your living room on Earth. Einstein asked the question that changed the world. Can you tell the difference? Can you, locked inside that windowless box, perform any experiment whatsoever that distinguishes between the rocket accelerating upward and the Earth pulling you downward? You feel weight on your feet. Objects fall. Pendulums swing. Springs compress. You measure the acceleration of a dropped object and find 9.8 meters per second squared in both cases. You measure it more precisely and still find no difference. Einstein said no. The two situations are physically identical, not merely similar, not merely hard to distinguish. Is identical. He called this the equivalence principle, and he later said it was the happiest thought of his life. Now, there is something hidden in this observation that most people walk right past. It has to do with a question that nobody asked for 200 years because the answer seemed too obvious. Why does everything fall at the same rate? Galileo demonstrated this around the year 1590. Drop a heavy rock and a light rock from the same height, and they hit the ground at the same time. Ignoring air resistance, a cannonball and a feather fall at exactly the same rate. Everyone knows this, but have you ever stopped to ask why? Why, in Newton's equation, the force of gravity on an object is proportional to its mass. A heavier object feels a stronger pull, but acceleration equals force divided by mass. So the heavier object also has more inertia, more resistance to being accelerated. The stronger pull and the greater resistance exactly cancel, and everything falls at the same rate. But why should they cancel? The mass that appears in the gravity equation, what physicists call gravitational mass, is a measure of how strongly an object generates and responds to gravitational fields. The mass that appears in Newton's second law, the inertial mass, is a measure of how hard it is to shove an object. These are logically different properties. There is no obvious reason they should be identical. And yet they are. The Hungarian physicist Loran Eötvös tested this with exquisite precision around 1906, using a torsion balance that could detect differences as small as a few parts in 100 million. Gravitational mass and inertial mass were the same as far as he could tell. Modern experiments have pushed the agreement to better than 1 part in 10 to the 13th. These two completely different concepts, the charge of gravity and the resistance to acceleration, are identical to at least 13 decimal places. In Newton's theory, this is a coincidence. A spectacular, unexplained, suspiciously perfect coincidence. In Einstein's theory, it is not a coincidence at all. It is inevitable. If gravity is not a force but the curvature of space-time, then every object follows the same geodesic regardless of its mass or composition. A ball of lead and a ball of wood follow the same path through curved spacetime because the path is a property of the geometry, not of the object. The mass of the falling object never enters the picture. Everything falls the same way because everything follows the same geometry. The equivalence of gravitational and inertial mass is not a lucky accident. It is a consequence of gravity being geometry. That is an enormously powerful argument. It takes one of the deepest unexplained puzzles of Newtonian physics and resolves it automatically as a side effect of the new theory. That is the hallmark of a correct idea. It seems like a modest observation at first glance. But Einstein was the kind of person who, when he found a loose thread, pulled it until the whole sweater unraveled. Let me show you what happens when you pull this thread. You are in your accelerating box. A laser on the left wall shoots a beam of light horizontally toward the right wall. From the perspective of someone floating outside, watching the box accelerate past them, the light travels in a perfectly straight line, but the box is accelerating upward. By the time the light reaches the right wall, the box has moved up a bit. From your perspective inside, the light enters on the left at a certain height and hits the right wall slightly lower. The beam curves downward. If acceleration is truly identical to gravity, then gravity must also bend light. Think about what that means. Light has no mass. In Newton's equation, one of the masses would be 0, and 0 times anything is 0. Newton says light should be completely immune to gravity. It should pass through a gravitational field like a ghost through a wall. Einstein says no. Light bends in a gravitational field. That is a prediction, a bold, testable, falsifiable prediction. In 1919, the British astronomer Arthur Eddington organized 2 expeditions to observe a total solar eclipse, one to the island of Principe off the coast of West Africa, and one to Sobral in northern Brazil. During the eclipse, when the sun's blinding light was blocked by the moon, Eddington photographed the stars that appeared near the edge of the sun. If Einstein was right, the sun's gravity would bend the starlight passing near it, making the stars appear to shift position slightly outward from their true locations. Eddington measured the shifts. They matched Einstein's prediction. Newton was wrong. The headlines were electric. Newspapers around the world reported that a theory which had stood for over 2 centuries had been overturned. Einstein became famous overnight. But the headlines only told part of the story. The bending of light was dramatic and made for great newspaper copy, but the more profound confirmation had already occurred in Einstein's study 4 years earlier. Remember Mercury, those stubborn 43 arcseconds per century that no one could explain. In November of 1915, Einstein finished the final form of his field equations. One of the first things he did was apply them to the orbit of Mercury. He calculated the precession of Mercury's perihelion in the new theory, and the answer came out to exactly 43 arcseconds per century. Exactly. Not roughly. Not approximately. The extra precession that had plagued astronomers for over half a century dropped out of the equations as naturally as a ball drops from your hand. Einstein later wrote that when he saw the result, his heart palpitated. He said he was beside himself with excitement for days. He knew in that moment, with a certainty that went beyond any experiment, that he had found the right theory. The geometry of space-time near the Sun is slightly different from what Newton assumed, and Mercury, closer to the Sun than any other planet, orbiting in the most curved region of the solar system, feels that difference most strongly. Its geodesic through space-time is not quite the ellipse Newton predicted. It precesses, and it precesses by exactly the amount that had been observed. After Eddington confirmed the bending of light, the case was overwhelming. But I still have not told you the real idea. I have spent all this time tearing down the old building. Let me show you the new one. Because it is breathtaking. Forget forces. Forget pulling. Forget invisible ropes stretching across the vacuum. Forget action at a distance. All of it. Gone. Mass warps time. Not metaphorically, literally, physically, measurably. The flow of time, the actual rate at which seconds tick by, is altered by the presence of mass. Take two identical atomic clocks, the most precise timekeeping instruments ever devised by human beings, accurate to 1 second in hundreds of millions of years. Put one on the floor of your room and one on the ceiling. Wait, not long, a few days will do if your clocks are good enough. The clock on the floor will have fallen behind. It will read a slightly earlier time than the clock on the ceiling. The difference is absurdly small, measured in femtoseconds, a femtosecond being 1/1,000,000th of a billionth of a second. But it is there, it is real, and it is not a flaw in the clocks. Time itself runs slower, closer to the Earth. This was first measured in 1959 by Robert Pound and Glenn Rebka at Harvard. They sent gamma rays up a tower about 22.5 meters tall and measured the shift in frequency. Gamma rays climbing up out of the Earth's gravitational field lost energy. Their frequency dropped just as a ball thrown upward loses kinetic energy and slows down. But for light, losing energy means decreasing frequency, which means time is running faster at the top. The measurement matched general relativity to within 10%, and later refinements brought the agreement to better than 1%. This is not exotic speculation. You rely on this effect every day and do not realize it. The Global Positioning System uses satellites orbiting about 20,200 kilometers above the Earth. At that altitude, gravity is weaker, and the clocks on the satellites tick faster than clocks on the ground by about 38 microseconds per day. The system's engineers have to correct for this, or your GPS position would drift by roughly 10 kilometers per day. Every time your phone tells you which street to turn on, it is relying on Einstein's theory of curved spacetime, not Newton's law of gravity. Now let me show you why this matters. Why the warping of time is not just a curious side effect of gravity, but is gravity. Every object in the universe is always moving through space-time. You are doing it right now, sitting in your chair, motionless in space. You are nonetheless hurtling forward through time. Your watch ticks, your cells age. You move through the time direction at the maximum possible rate. In special relativity, your total speed through space-time is always the same, the speed of light. This sounds bizarre, but it is a mathematical fact of Einstein's framework. When you sit still in space, all of your space-time speed goes into the time direction. When you start walking, running, flying, some of that speed shifts from the time direction into the space direction. That is why moving clocks run slower than stationary ones. Motion through space steals from your motion through time. Now, imagine you are holding a tennis ball near the ceiling of your room. The ball is not moving through space. All of its space-time motion is in the time direction. But time is not flowing at the same rate everywhere around the ball. Closer to the Earth, time runs a tiny bit slower. Farther from the Earth, time runs a tiny bit faster. There is a gradient, a slope, in the rate of time. What does a free object do in a region where time flows at different rates? It follows the straightest possible path through the geometry. Physicists call such a path a geodesic. On a flat sheet of paper, the straightest path between 2 points is a straight line. On the curved surface of the Earth, the straightest path between New York and London is a great circle arc that swings north, passing near Iceland. It looks curved on a flat map, but on the sphere itself, it is the straightest path there is. Your tennis ball. The moment you release it, follows a geodesic through the curved space-time near Earth. The gradient of time, slower below and faster above, tilts the geometry. The straightest path through that tilted geometry curves downward. The ball accelerates toward the floor. No force pulls it. Nothing grabs it. Nothing reaches across space and tugs. The ball is simply following the straightest line through the geometry it finds itself in, and that geometry, warped by the presence of Earth's mass, bends the straight line downward. Let me give you another picture that might make this click. Imagine two ants walking side by side northward, starting from different points on the equator of the Earth. They walk perfectly parallel, maintaining their heading due north. They are not trying to converge, they are walking in straight lines on the surface. But the surface of the Earth is curved, and the lines of longitude they are following converge toward the poles. Without either ant turning, without either ant feeling any sideways push, they get closer and closer together. If they walk far enough, they meet at the North Pole. An ant who does not know the surface is curved would say, "Some mysterious force pulled us together." An ant who understands the geometry of a sphere says, "No force at all. We were both walking straight. The surface itself brought us together." That is precisely the situation with gravity. Objects moving freely through curved spacetime converge toward each other. We watch them converge and say a force must be pulling them. Einstein says no, they are both moving straight. The spacetime itself brings them together. You experience this as the ball falling, as gravity. But the ball experiences nothing at all. If you were riding on the ball, you would be weightless. No sensation of force, no pressure, no pull. You would float, exactly like an astronaut in orbit, exactly like someone in deep space, far from any mass. The ball is in the most natural state of motion the universe allows, free fall along a geodesic. You, standing on the floor watching the ball drop, are the one experiencing a force. The floor pushes on your shoes push on your feet. Your skeleton transmits that push upward through your body. You feel heavy, you feel weight, and what you are feeling is the electromagnetic repulsion between the atoms in the floor and the atoms in your shoes, preventing you from following your own geodesic, which would carry you into free fall toward the center of the Earth. In Newton's picture, the ball is being forced, and the person on the ground is at rest. In Einstein's picture, it is exactly the reverse. The ball is free, unforced, natural. The person on the ground is being violently accelerated upward, pushed away from their natural trajectory by the rigidity of the ground beneath them. This is not a reinterpretation. This is not a different way of looking at the same thing. The two pictures make different predictions, and Einstein's predictions are the ones that match experiment after experiment. When a skydiver jumps from an airplane for those long seconds before the parachute opens, she is in the most natural state of motion in the universe. She is following a geodesic through curved space-time. She is free. The wind resistance complicates things, but in principle, without air resistance, free fall is freedom. The moment she lands, the ground grabs her, accelerates her, shoves her off her geodesic. She feels the jolt. She feels weight. She is no longer free. Gravity in this picture is not a force at all. It is what happens when you remove every force and let an object coast through the shape of space-time. It is the background. It is the geometry of the stage. Electromagnetism is a force. The nuclear interactions are forces. They deflect objects from their natural paths. Gravity does no such thing. Gravity is the natural path. I should mention something about a popular analogy that you have probably seen because it misleads people badly. You know, the picture of the rubber sheet with a bowling ball on it making a dip and a marble rolling around the dip. That analogy has two serious problems. First, it uses gravity to explain gravity. The marble rolls into the dip because of the Earth's gravity pulling it downward. That is circular. Second, it only shows the curvature of space, not time. And as I have been telling you, the curvature of time is the dominant effect. The bowling ball on the rubber sheet is a useful starting image, but if you stop there, you will never understand what general relativity is actually saying. The real curvature is in how fast clocks tick at different locations. You cannot see that on a rubber sheet. You have to think about it, and thinking about it is harder but infinitely more rewarding. Now, the obvious question, why does mass create this curvature? Why does putting a big ball of rock and iron in one place change the rate at which nearby clocks tick? I want to be honest with you here because I think you deserve honesty more than comfort. We do not fully know what Einstein gave us as a relationship, expressed in what is called the Einstein field equation. On one side of the equation sits the curvature of spacetime, encoded in a mathematical object called the Einstein tensor. On the other side sits everything that generates curvature: mass, energy, momentum, pressure, stress, all bundled into something called the stress-energy tensor. The equation says curvature equals a constant times the stress energy. The constant involves Newton's gravitational constant and the speed of light. This equation tells you how to calculate the curvature given any arrangement of mass energy. It works. It works spectacularly. It predicted gravitational waves, gravitational lensing, the bending of light, the precession of Mercury, the expansion of the universe, black holes, the slowing of time near massive objects, and on and on. Every prediction has been confirmed, but the equation does not tell you the mechanism. It does not explain what spacetime is made of, or why mass energy couples to its geometry in this particular way. Think of it like this. If you put a bowling ball on a waterbed, the waterbed sags. You can write an equation relating the weight of the ball to the depth and shape of the sag. That equation works, but the reason the waterbed sags is because it is made of a flexible membrane filled with water, and the ball compresses the membrane under its weight. You understand the mechanism. Material flexes under load. What is the mechanism for spacetime? What is spacetime made of, that it bends under the load of mass energy? Nobody knows. This is one of the great open questions in physics. Some suspect the answer lies in quantum gravity, perhaps at the smallest conceivable scales, at the Planck length, roughly 1.6 times 10 to the minus 35 meters. Space-time dissolves into something more fundamental. Quantum bits of information, threads of entanglement, loops, foams, networks. The smooth geometry we experience might emerge from a deeper, grainier quantum structure, the way the smooth surface of a lake emerges from trillions of water molecules, none of which individually look anything like a smooth surface. If so, the link between mass energy and curvature might emerge naturally from the rules of that deeper structure. But we do not have the theory yet. Whoever cracks this problem will be remembered alongside Newton and Einstein themselves. Let me tell you a few more things we do know, because they are astonishing, and they deepen the picture in ways that shock most people. Mass is not the only thing that curves spacetime. Energy does too. All forms of energy. A box filled with hot gas weighs slightly more than the same box filled with cold gas. Not because of extra atoms, the atoms are the same, but the kinetic energy of the faster moving gas molecules in the hot box contributes to the gravitational field. Light has no mass, but light has energy, and a box full of light weighs more than an empty box by a tiny, tiny amount. In everyday life, these contributions are laughably small, but in extreme environments, they become significant. Pressure also gravitates. This is something Newton never dreamed of. In the cores of neutron stars, matter is compressed to incredible densities, hundreds of millions of tons squeezed into each cubic centimeter. The pressure needed to support the star against collapse is enormous, but that pressure is itself a source of gravity. It adds to the curvature, which makes the star need even more pressure, which adds even more gravity. A vicious feedback loop. Above a certain mass, roughly 2 to 3 solar masses, this loop runs away. No physical process in the known universe can generate enough pressure to halt the collapse without that pressure making the collapse worse. The star falls through its own event horizon. It becomes a black hole. The very strength it uses to resist gravity becomes a source of more gravity. That is one of the most remarkable and chilling predictions in all of physics. And space-time curvature does not merely sit there, static and fixed. It moves, it ripples. If you suddenly shake a massive body, a ring of curvature propagates outward at the speed of light. These ripples are gravitational waves. Einstein predicted gravitational waves in 1916. For nearly a century, they remained theoretical, too faint to detect. Many physicists doubted we would ever measure them directly. The technology needed was almost absurdly demanding. You would have to build a detector sensitive enough to measure a change in length smaller than 1/10,000th the diameter of a proton. That is like measuring the distance to the nearest star and noticing a change the width of a human hair. Nobody thought it was possible for decades. Then, on September 14, 2015, at 5:51 in the morning Eastern Time, the LIGO Observatory recorded a signal. Both detectors, one in Livingston, Louisiana, and the other in Hanford, Washington, picked up an identical vibration within 7,000ths of a second of each other. Exactly the delay you would expect for a signal traveling between the two sites at the speed of light. Two black holes, one about 36 times the mass of our Sun, and the other about 29 times, had been spiraling toward each other for millions of years. In the last fraction of a second, they merged. The collision converted about 3 solar masses worth of matter directly into the energy of gravitational waves. Those waves rippled outward at the speed of light, and 1.3 billion years later, washed over Earth. They stretched and compressed the 4-kilometer arms of the detector by roughly 1,000th the width of a proton, and the instrument measured it. Newton's gravity has no waves. It cannot. In Newton's theory, gravity acts instantaneously everywhere. If you move the sun, Pluto knows at once. That violates everything we know about the speed of light. Einstein's theory does not have this problem. Gravity propagates. It has a finite speed. Space-time is dynamic, alive, rippling across the universe like waves on a dark ocean. Now let me drive home the point I have been building toward because it is the most important insight in all of general relativity, and it is the one most people miss. Time, not space, is the primary source of what you experience as gravity. Yes, mass curves space too. The geometry of space near the Sun is slightly non-Euclidean. Straight lines through space near the Sun are very slightly deflected. This is what causes the bending of starlight that Eddington measured. But the curvature of space is a relatively small effect for anything moving slowly compared to light. And everything in your daily life moves slowly compared to light. A car on the highway is crawling at a few 100,000ths of the speed of light. Even the fastest human-made object moves at less than 1% of the speed of light. For slow-moving objects, the curvature of time completely dominates. The time component of space-time curvature is what produces virtually all of what you experience as gravity standing on the surface of the Earth. Objects fall not because space is curved, but because time is curved. When you throw a ball straight up, it rises, slows, pauses, and comes back down. In Newton's picture, gravity pulls it back. In Einstein's picture, here is what is happening. The ball, the instant it leaves your hand, enters a geodesic through space-time. Space-time near Earth is curved, and the curvature is overwhelmingly in the time direction. The gradient of time flow, slower near the surface and faster higher up, shapes the geometry so that the straightest possible path through space-time for the ball is a parabolic arc that curves back down. Not because a force turns the ball around, because the geometry of time creates a landscape in which that arc is the straightest line. If time flowed at the same rate everywhere, if there were no gradient, the ball would sail upward forever. Nothing would curve its path. It is specifically the slope in the river of time, slightly slower below your feet and slightly faster above your head, that creates the effect we call gravitational acceleration. Let me put a number on it, so you feel how small the cause is, and how large the effect. The difference in the rate of time between your head and your feet, over a height of about 1.8 meters, is roughly 2 parts in 10 to the 16th. That is a difference in clock rate of about 0.00000000000000000002%. And yet that infinitesimal gradient applied to an object moving through time at the speed of light produces an acceleration of 9.8 meters per second squared. A strong enough pull, or rather push, to pin you to the ground, break bones if you fall wrong, and shape the orbit of every planet in the solar system. The leverage of time is extraordinary. A whisper of temporal curvature produces what feels like an overwhelming force. The center of the Earth is younger than the surface. By about 2.5 years. Given the Earth's age of 4.5 billion years, time has been running slower at the core, under the immense gravitational field of all the mass above, for as long as the planet has existed. The core is literally, physically, measurably younger than the crust. The difference exists, and it exists because time near mass runs slow. Let me take you to the extreme case, because extremes are where you see the architecture most clearly. A black hole is not an object. It is a region of space-time. As a region where the curvature is so severe that all geodesics point inward. Once you cross the boundary called the event horizon, there is no outward direction. Not in space, not in time. The mathematics of general relativity show that inside the event horizon, the inward radial direction and the forward time direction swap roles. Falling toward the center of the black hole is no longer moving through space. It is moving through time. You cannot stop your descent toward the singularity for the same reason you cannot stop the arrival of tomorrow. It is in your future. The geometry of space-time inside the horizon has folded the spatial direction inward into a temporal direction. Approaching the singularity is as inevitable as the passage of time. Light cannot escape a black hole, not because gravity pulls light back, but because there are no outward-pointing paths through space-time. Every trajectory, every geodesic, whether followed by light or by a spaceship, curves inward. The geometry is closed, like a one-way street with no exits. We have observed these objects. We have detected gravitational waves from black hole collisions. We have imaged the glowing shadow of the supermassive black hole at the center of galaxy M87, a monster about 6.5 billion times the mass of our Sun, surrounded by a swirling ring of superheated gas orbiting at nearly the speed of light. That image, released in 2019, is not a simulation or an artist's rendering. It is a photograph of curved space-time at its most extreme, captured by linking radio telescopes across the entire planet into a single Earth-sized detector. These are not fantasies, they are confirmed predictions of what happens when space-time curvature reaches its most extreme. And every one of them, every gravitational wave, every bent beam of starlight, every precessing orbit, every ticking difference between clocks at different altitudes, tells the same story. Mass-energy curve, space-time, curved space-time tells objects how to move. And the thing we have called gravity for 3 centuries is nothing more and nothing less than the shape of time. And this brings me back at last to the question in the title. Why does mass create gravity? The truthful answer requires some patience. Mass is a form of energy. Einstein showed that with the most famous equation in physics, energy equals mass times the speed of light squared. Mass and energy are the same thing, measured in different units. And energy in all its forms is what appears on one side of Einstein's field equation, telling spacetime how to curve. Mass, kinetic energy, thermal energy, pressure, stress, light, all of it contributes to the curvature of spacetime. The field equation is not derived from something more basic. It is proposed, constrained by mathematical consistency and physical reasoning, and then tested against nature. Every test confirms it. But the question, why does energy curve spacetime, is a question the equation does not answer. It describes the relationship. It does not explain the cause. Perhaps the cause lies in a quantum theory of gravity we have not yet found. Perhaps spacetime is emergent, and at the deepest level what we call curvature is a statistical property of some quantum system, the way temperature is a statistical property of molecular motion. Temperature is not a thing, it is a summary of how fast many particles are jiggling. Maybe curvature is a summary of something even more fundamental, something to do with quantum information and entanglement, things we are only beginning to understand. Or perhaps the Einstein field equation is fundamental, and asking why mass curves spacetime is like asking why 2 and 2 make 4. Perhaps some truths are bedrock, we do not know which it is. And I think there is something beautiful about that. Here is what we do know, and it is enough to reshape how you see everything around you. Nothing pulls on anything. Nothing reaches across empty space to grab anything. There are no invisible ropes. The presence of mass and energy alters the rate at which time flows. Objects left entirely to themselves follow the straightest possible paths through that altered flow of time. Those paths curve toward the mass. We see the curving and call it falling. We feel the resistance of the ground and call it weight. We see the orbits and call it gravity. But none of it is a force. It is geometry. It is the shape of time itself, responding to the presence of energy. Every time you drop a cup, the cup is not being pulled toward the floor. The cup is coasting through warped time, tracing the most natural trajectory that the geometry of the universe permits. The cup is free. You, standing there watching, are the one being pushed. You are being shoved upward by the electromagnetic forces in the floor, forced away from the geodesic that would carry you into free fall. The sensation of weight is not gravity pulling you down. It is the ground accelerating you up. And And the deepest puzzle of all, the one physicists have been circling since the 1920s, is this: if gravity is geometry, might the other forces be geometry too? Kaluza and Klein proposed in 1921 that electromagnetism might be curvature in a fifth dimension of spacetime. String theory extends the idea to 10 or 11 dimensions. None of these proposals have been confirmed. But the deep suspicion that all forces are secretly geometry, that everything in the universe reduces to the shape of some high-dimensional structure, that suspicion started here. It started with gravity. It started with Einstein's realization that a falling apple is not being pulled down. It is simply free. One more thought. Newton watched an apple fall and asked what force pulled it. That question led to the greatest scientific equation of the 1700s, and it dominated physics for 2 centuries. But the question contained a hidden assumption. It assumed something must have pulled the apple. Einstein looked at the same apple and asked a different question entirely. He asked, what if no force pulled it at all? What if the apple is doing absolutely nothing? What if the apple is free, and the ground is the thing in motion? It sounds like a trick, a word game, but it is not. It is a total reconstruction of what space and time are, what motion is, what force is, and what it means for one piece of the universe to influence another. The apple in free fall is tracing the straightest line through reality, and reality near a massive body is bent. Mass does not create a force called gravity. Mass warps time, and warped time is what we have been calling gravity for 300 years. Think about what this means for every moment of your life. From the day you were born to this very second, you have never once experienced the force of gravity. What you have felt continuously, without interruption, is the electromagnetic force of solid matter pushing against you, preventing you from doing what you naturally want to do, which is to fall freely through curved space-time. The weight you feel in your legs when you stand, the pressure on your back when you lie down, the jolt when you land after a jump, none of that is gravity. All of it is electromagnetism. The atoms in the ground refusing to let the atoms in your body pass through. Gravity is what you feel when you feel nothing. Gravity is the experience of the skydiver before the parachute opens. Gravity is the astronaut floating in the space station. Gravity is weightlessness, and what we have been calling the feeling of gravity our whole lives is actually the feeling of being prevented from following gravity. The language of everyday life has it exactly backward. We say we feel gravity. We never feel gravity. We feel the resistance to it. If that does not change the way you feel the ground beneath your feet, then I have not done my job. But I think it does. I think the next time you drop something for just a moment, you will see it differently. You will see the object moving freely while the world around it resists. Here is what I want to know from you right now, sitting wherever you are, feeling the chair press against you, knowing that the ground is accelerating you upward, that free fall is freedom, and that gravity is the shape of time. What does that change about how you understand your own place in the universe? Sit with that question. And when you have something, tell me